Hello and welcome to the lecture. Now, during this lecture, we're going to continue reviewing the lean tools and building blocks. And one of my favorite tools is error-proofing. It used to be called foolproofing, can't call it that anymore. And it's sometimes called mistake-proofing. We're going to use the term error-proofing, or in Japanese terms, poka-yoke. So the topics for the lecture are as follows. We have what is error-proofing. Let's talk about the definition of error-proofing. Then we're going to look at this concept introduced by an author, Donald Norman, called knowledge in the world versus knowledge in the head. We look at some product and process design, error-proofing, and then we'll finish up with error-proofing and statistical process control and why they work well together. Now, if you were working on a Six Sigma project using the DMAIC methodology, error-proofing would fit into the improve phase. There are statistical tools you could use, such as design of experiments, but the qualitative tool best to use would be error-proofing. So what is error-proofing? It's the use of process or design features to prevent errors or their negative impact. As I said, when the Japanese first introduced this as poka-yoke, that was a term for avoiding inadvertent errors. But ultimately, we want to come up with solutions that are simple and innovative. Simplicity is the greatest form of innovation, effective, and ideally low cost. Let's look at an early example of error-proofing. Now, this example came from a munitions factory during World War II. So you can see here a grenade, and the grenade is being assembled on a production line. So the operator is assembling the final step of the grenade here, where they insert a pin into the detonator. Now they have an inspector behind them and a second quality inspector to ensure that the process is done correctly. Now in this case, the grenade is live after the pin is inserted. So it's very important that the pin insertion step is done correctly. If the pin is not put in, then the grenade can fall off the table, as you'll see here, and it will cause an explosion. So this is what happened in this particular munitions factory. What they did then is they decided that they would error-proof the process. So they designed a support holder which only allowed the grenade to be passed on to the next process step if the pin was inserted. So as you can see here, the only way the grenade can be passed on to final packaging is if the pin is inserted. This error-proofing was so successful they were able to get rid of the additional quality inspectors. And the example shown here is one of the first known examples of error-proofing. It also meets the requirement of a successful poka-yoke or error-proof, which is simplicity, effectivity, and low cost. Another system for preventing errors you may be familiar with is the Swiss cheese model. And we have a series of control systems, which are these blue controls here. And ideally, if errors occur out here, we need to have the system controls in place so that they don't cause harm. And you can see here, here's an error and this control system catches it. Here's another error and the first two control systems don't capture it. So it's stopped here. But in a rare case, maybe the error will cause harm. And ideally what you want to do is reduce the number of errors going into the system, but also have enough controls in place so that the error doesn't cause harm or doesn't cause defects. So why use error-proofing? Well, we can reduce customer complaints in a manufacturing environment, reduce cost of scrap material, reduce time spent on rework and repairs. We can also use it to avoid damage to equipment, avoid defects being passed on to the next process step. We can fix the root cause of the problem, and really what's very useful in error-proofing is that it can act as a 100% inspection point, which is quite rare to get. Most inspection stations have a tolerance. But if you can create a 100% inspection point, and we look at some examples, that is a real benefit of error-proofing. Now, moving on to another book that I wanted to talk about. This was originally published by Don Norman as The Psychology of Everyday Things. It's been republished and reprinted as The Design of Everyday Things, and it looks at good product and process design. But what Don Norman really brought out in this book was this concept of putting knowledge in the world versus knowledge in the head. So what does that mean? This is typically we would improve our standard operating procedures, we would retrain people, we would recertify skills, and we would manage and enhance attentiveness in the operation. And they're all important, but what we really want to do is provide clues what to do in the process or in the product. We embed those details in the process, so that frees the mind to consider a bigger picture and facilitates knowledge work. So let's look at some examples of that. So as you can see on these two examples of hobs, we have natural mappings. So hob A is a one-to-one mapping if we want to turn on the ring, whereas over hob B we don't really know. Now there is a design constraint that uses up some very valuable space here, but you can see the concept that Don Norman was describing of putting knowledge in the world. What Don Norman is most famous for is the design of doors. And his argument is that you should be able to walk up to a door. There should be no sign on the door. The door should be designed such that you understand exactly whether it opens by a push or a pull. So here you can see we see hinges on the right. We see a handle, so we expect this to be a pull, but it may not be. Similarly with door B, we see a push, so we expect it to push, and usually it does, but you can see some bad designs that would have a plate here, and it doesn't always open the way you think it opens. And then finally, door C is maybe a sliding door. Visibility and feedback are also very important. So you can see here, where should the dial be? It should be in the green zone. If it's not, then you need to fix it or address it or call for help. Other examples in design error-proofing, an interference pin. So there's only one way for this part to go onto the machine. It cannot go on this way. So this is a simple, inexpensive and effective error-proofing or poka-yoke solution. Other examples in software. If you're entering a credit card, the numbers populate onto the screen. This pops up and you type in the expiry date and the 3-digit code. And some newer examples now, you can see over here, you are asked to take a picture of your credit card and it automatically populates the website with your credit card details. Another book I would recommend is one by Steve Krug, and it's called Don't Make Me Think. And really, it's the seminal text on web usability. So when you go to a website, everything is where it's supposed to be. If you're going on a hotel website, you don't have to search for the book now button to book a hotel room. So very worthwhile if you work in that space to get that book. Other everyday examples. Again, you don't need to read a standard operating procedure to cross the road, particularly in big cities. Tells you whether to look left or look right. Petrol cap, the nozzle will only accept petrol. There's a tether, prevent loss of the petrol cap, and there's a ratchet so you don't over tighten it. And these have been improved subsequently, whereby you don't even have a petrol cap, it's integrated into the door, or if you have EV, you don't have petrol anymore. Other examples, the TIG cup, allow easy passing of a cup from person to person, or Apple's maybe not so new charger now can be inserted anyway. So this would be another concept in error-proofing called de-skilling. Your microwave oven won't work until the door is shut, either will your washing machine with interlocks. Also for safety, it won't allow the door to be opened until 30 seconds after the cycle is complete. In the US, the FDA have mandated where drugs sound very similar that you can use tall man lettering. So you can see here hydralazine and hydroxyzine. Now they shouldn't be the same color, you could argue, but you can see certain letters are capitalized to help distinguish between one drug and the other, such as Zyprexa here. The Prexa is capitalized. So the cost of Poka-Yoke devices, as you can see, over 50% are less than $100 or €100. So ideally in that space, you can get more expensive ones, and in that case, a cost-benefit analysis would have to be done. If we look at error-proofing and statistical process control, really SPC is really good at detecting shifts in the process, but changes to the process must be ongoing to be readily detected, whereas human errors are rare intermittent events. So you really want to use both. So I'll give you an example. Let's say you're having an operator mill a slot here. It's got a 25 millimeter width. You have an upper control limit and lower control limit. So if the width of this slot is drifting too low or too high, you can pick that up. But if the operator omits to mill the slot, then that probability is either 0, it doesn't happen, or it does happen. So we might want to error proof that as well as using SPC. So in summary, error proofing reduces wrong actions, makes it possible to reverse undue actions or make it harder to do what cannot be reversed, makes it easier to discover the errors that occur and make incorrect actions correct.